using seismometers and other monitoring devices to detect any signs of increased seismicity or fault movement. From a public outreach perspective, scientists are actively engaging with stakeholders to communicate the significance of the discovery and its implications for earthquake preparedness. Educational initiatives, public forums, and media outreach campaigns are being employed to raise awareness about seismic risks and promote community resilience strategies. Seismic science and fault dynamics. Seismic science, the study of earthquakes and fault dynamics, plays a crucial role in understanding the Earth's tectonic processes and mitigating the risks associated with seismic hazards. At the heart of this field lies the exploration of fault generates stress along fault lines, accumulating strain until it is released suddenly in the form of an earthquake. Seismologists employ a variety of tools and techniques to study fault dynamics. One of the primary methods involves the deployment of seismometers, instruments that detect and record ground motions caused by seismic waves. By analyzing the arrival times and characteristics of these waves, scientists can pinpoint the location, depth, and magnitude of earthquakes, providing insights into the behavior of faults. Key to understanding fault dynamics is the concept of fault slip, which refers to the relative movement of rocks on either side of a fault plane. This movement can occur in different ways. Along strike-slip faults, rocks move horizontally past each other. In dip-slip faults, movement is vertical, either up or down, while others may release stress more frequently through smaller events. This segmentation complicates seismic risk assessments, but provides critical insights into earthquake patterns and potential impacts on local communities. Recent advances in technology have revolutionized the field of seismic science. High-resolution satellite imagery, LiDAR, light detection and ranging surveys, and GPS, global positioning system measurements, allow scientists to map fault systems with unprecedented detail. These tools enable researchers to monitor subtle changes in fault geometry and strain accumulation over time, enhancing our ability to forecast seismic activity and improve early warning systems. The dynamics of fault systems are also influenced by factors such as rock type, fault geometry, and regional stress fields. Geologists conduct along the San Andreas Fault line are crucial for understanding and preparing for potential earthquake events that could impact millions of people in California and beyond. The San Andreas Fault is a major tectonic boundary between the Pacific Plate and the North American Plate, running roughly 800 miles, 1,300 kilometers, through California. It is known for its potential to produce large and destructive earthquakes due to the accumulated strain along its length. Monitoring of the San Andreas Fault involves a range of techniques and technologies aimed at detecting and studying subtle changes in the Earth's crust that could indicate increased seismic activity. Seismometers, which measure ground motion caused by earthquakes, are strategically placed along the fault and throughout the region to monitor for any signs of seismicity. These instruments, which occur between major earthquakes, and provide insights into the buildup of stress along the fault line. In addition to instrumental monitoring, geological field studies play a crucial role in understanding the historical behavior of the San Andreas Fault. Geologists analyze rock formations, fault scarps, and other geological evidence to reconstruct past earthquakes and assess their magnitude and frequency. This historical context helps scientists model potential future earthquake scenarios and estimate the likelihood of different seismic events. Mitigation efforts focus on reducing the impact of earthquakes on communities and infrastructure through preparedness, engineering practices, and public education. Building codes in California are among the strictest in the world, requiring structures to be designed and constructed to withstand alerts and information to the public, government agencies, and first responders in the event of significant seismic activity. Early warning systems can provide seconds to minutes of advance notice before shaking reaches populated areas, allowing individuals to take protective actions and critical infrastructure to automatically initiate safety protocols. Potential role of dried-up lakes. The potential role of dried-up lakes in the context of seismic activity along the San Andreas Fault line is a topic that intersects geology, hydrology, and seismology, offering insights into how changes in water levels can influence tectonic processes and earthquake hazards in California and beyond. Dried-up lakes, also known as paleo lakes, are ancient lake beds that once held, preserving a chronological archive of environmental changes and geological events. By studying these sediments, scientists can reconstruct past seismic activity, including the frequency, magnitude, and intensity of earthquakes that have affected the region over centuries or millennia. For instance, seismic waves generated by large earthquakes can liquefy sediments at the bottom of lakes, causing them to settle in distinct layers that are recognizable in geological records. These sedimentary disturbances, known as turbidities, serve as geological fingerprints of past seismic events and help researchers establish a timeline of earthquake occurrences. In addition to sedimentary records, dried-up lakes offer insights into the hydrological conditions that existed during different periods of geological history. Changes in water levels affecting the stress regime along nearby fault systems. This dynamic interaction between water levels and tectonic forces underscores the complex relationship between hydrology and seismicity. From a hazard perspective, understanding the role of dried-up lakes in seismic activity can inform risk assessments and mitigation strategies in earthquake-prone regions. Areas near paleo lakes may exhibit heightened vulnerability to ground shaking or ground failure during earthquakes, depending on the geological characteristics of the sedimentary deposits and the proximity to active fault lines. Furthermore, paleoseismology studies, which involve the analysis of ancient earthquake evidence preserved in geological formations like dried-up lakes, contribute to refining seismic hazard assessments. By combining paleo lake data with other geological, the San Andreas Fault, and other tectonic zones. By examining past earthquakes and societal responses, we can glean valuable lessons that inform current preparedness efforts and shape future resilience strategies. California's seismic history is marked by several significant earthquakes that have shaped its landscape and communities. One of the most devastating earthquakes in the state's history occurred on April 18, 1906, when a massive magnitude 7.8 earthquake struck the San Francisco Bay Area. The earthquake and subsequent fires caused widespread destruction, claiming over 3,000 lives and leaving more than 200,000 people homeless. This event remains a poignant reminder of the destructive potential of seismic activity and underscored the need for effective disaster preparedness and response measures. An event highlighted the vulnerability of urban infrastructure and spurred advancements in building codes and retrofitting practices to enhance seismic resilience. Historical earthquakes in California provide critical insights into seismic risk assessment and preparedness. By studying the geological characteristics, ground motions, and societal impacts of past earthquakes, scientists and emergency managers can better understand the dynamics of seismic events and improve mitigation strategies. For instance, paleoseismology, which examines prehistoric earthquakes through geological evidence, helps identify earthquake recurrence patterns and assess the potential magnitude of future events. Preparedness efforts in California have evolved significantly over time in response to historical earthquakes. The state has implemented in enhancing earthquake preparedness, Initiatives such as earthquake drills, community resilience programs, and dissemination of earthquake safety guidelines help educate residents about protective measures and evacuation procedures. These efforts aim to empower individuals and communities to respond effectively in the event of a seismic emergency, potentially saving lives and reducing the impact on infrastructure. Technological advancements have further enhanced earthquake monitoring and early warning capabilities. Seismometers deployed throughout California continuously monitor ground movements, providing real-time data that informs emergency response actions. Early warning systems, such as Shake Alert, utilize this data to alert residents and businesses seconds to minutes before shaking begins, allowing for rapid protective action. While you are still here, make sure to click the video on your screen for more quality content.